Hello, everyone. This is Mr. Rancourt, and I'm here to show you distance versus time graphs. With that being said, um, I've given you a piece of graph paper, and on the back, I want you to flip it over so that we can write some notes. Okay, and I want you to label it distance versus time graphs. And I'm sorry, I'm on a tray, so it's a little wobbly, and so my handwriting is not as neat as it usually is when I'm writing notes. So I will do my absolute very best. Distance versus VS. All right. So the purpose of a distance versus time graph is this. And we're going to write this. The purpose is to show how far something travels. To show how far something travels over time. To show how far something travels over time. And there's some key things that I need you to remember each time you look at a distance versus time graph. This is ideas, sorry. Again, I apologize for my handwriting. Some key ideas. First of all, you know on a graph that there's an x and y axis. The y axis is the vertical axis. So in this case, on the y axis, we show distance. So distance, the y axis. Okay. And this shows us how far the object is moved. How far the object has moved. And I would say from its starting point. From its starting point. That's the y-axis, the vertical axis. Time is showed on the x-axis. Time is showed on the x-axis, and that tells us um, how long the object has been moving. How long, or for how long, I should say, for how long the object has been moving. It might tell us seconds, it might tell us minutes, it might tell us hours, so on and so forth. Okay? Now, draw a line real quick. Sorry about this. Some key things that you should know right away. Go ahead and draw this real quick, just a freehand one, just a real quick freehand. So when you have a graph like this, yeah, and it's going up on the angle, what that means is that the object, I'm gonna draw a little bracket, the object is moving, the object is moving at a consistent or same speed. And I'm going to show you that here in just a second. We're going to calculate it to prove that this is correct. Okay, so the object is moving at consistent speed. When it has a straight line like this, um, moving up on the upper diagonal. If it is, for instance, flat like this, yeah, that means the object is not moving. Let's draw another bracket down, pointy down in. Okay, means the object is not moving. And if you're like, well, how is that? I'm going to show you that in just a second. I'm going to draw on the other side. Last one. If the object is going on the downward angle, like this, what it does is it tells us that the object is going back towards the starting point or going back home. So the object is going back B-A-C-K. I'm sorry, this tree is horrible. It's going back to its starting point. Going back to its starting point. Cool? And just so you know, the steeper the angle, the faster it's moving. And you know, we should probably write that real quick. I'm gonna do a little asterisk like this quickly, and just put a little asterisk right here. So the steeper the line, the faster the object is moving. The faster the object is moving. And again, I'm gonna prove that to you here in just a second mathematically with a graph. Cool? On your test, it's gonna show you things like this, and it's going to ask you describe the object's motion. If it's like this, you're gonna say it's moving at the same speed. If it looks like this, the object is not moving. The object, excuse me, if the graph looks like this, a distance versus time graph, the object is going back to its starting point. Back to its starting point. Okay? So get this into your, or write this on the back of this graph piece paper, graph paper, and then come up and show it to me, and I'll give you credit for it. Thanks.